Hello friends and welcome back to my channel. In this video I will present you an old-style electronic project. What I mean is that instead of the usual Arduino, I will make use of generic ICs. Nowadays these devices have been superseded by microcontrollers, but they are still very interesting and knowing their functioning is important from a didactical point of view. Before we continue, I would like to invite you to subscribe to my channel and also to activate the notification bell in order to stay informed on upcoming videos. So let's start with the intro, then we'll move on to the project description. For this project, I will use a CD4017. This device belongs to the so-called CMOS 4000 family. This name derived by the fact that all the ICs of this series are identified by a 4-digit number starting with 4. Depending on the manufacturer, the same device can have different names. This one, for example, is produced by ST Microelectronics and is labeled HCF4017. However, you can find the same IC with names like CD4017 or HEF4017, as in the case of this one produced by Texas Instruments. The ICs of the 4000 series can function with a wide range of supply voltages, generally from 3 to 15 volts. There are, however, some versions of these devices designed to be compatible with TTL voltage levels. In this case, the maximum supply voltage is 5 volts. The TTL versions have the same model number of their CMOS counterpart, but their name normally starts with prefixes like 54 or 74. Here you can see the datasheet of a TTL version of the CD4017, the 74HCT4017. If you use this version, you must ensure that the power supply doesn't exceed 5 volts. The 4000 family comprises several models, ranging from simple logic gates to ICs capable of complex functions, such as counters, dividers or display drivers. So let's see how the 4017 works. Inside this IC we find a 5-stage Johnson counter, that is a particular type of binary counter, and a decimal decoder. When we apply a signal to the clock input, the Johnson counter will increase at every pulse, going from 0 to 9, and then restarting. The decimal decoder then, according with the counter, will sequentially set its 10 outputs at a logic high level. Here we can see the pinout of the IC. Pin number 8, labeled VSS, is the negative supply terminal, while pin number 16, named VDD, is the positive. Pin number 14 is the clock input, while pin 15 is the counter reset input. Applying a low level to this terminal will force the counter to restart from 0. The output pins are labeled from Q0 to Q9. Pay attention because their order is different from that of the IC pins numbering. So let's see a simple circuit to test the IC functionality. As we have seen, the power must be applied to pins number 8 and 16. Now we can connect the anodes of some LEDs to the outputs. In this case, for simplicity, I will use only 5 LEDs, connecting them to the outputs from Q0 to Q4. The cathodes of the LEDs can be joined together and connected to ground via a single resistor. The value of this resistor depends on the supply voltage. For a 9V supply, you can use a value of 470 or 560 ohms. Having connected only some outputs, we now need to ensure that the counter restarts from the beginning after the last LED. To do so, we must connect the first unused pin, in this case Q5, to the reset input. In this way, when the counter reaches 5, it will restart from 0. Now, for the counter to work, pin number 13 must be connected to ground. I didn't mention it before, but this is the clock inhibit pin. And here is the circuit built with real components. We are now ready to perform a first test, and as you will see, there will be some surprises. You have surely noticed that I left the clock input disconnected, so we expect that the counter will remain in a steady state. However, as you can see, when I apply power, all LEDs begin to turn on sequentially at a very high speed. This is due to the fact that the clock input has a very high impedance, and when left floating, it becomes very sensible to interference. In this case, probably, the field generated by the electric system is sufficient to stimulate the counter. To solve this problem, I put a 10K resistor from pin 14 to ground, in order to keep it at a fairly low level. In this way, the counter remains as expected in a steady position. And now I will try to stimulate the clock input by briefly touching it with a jumper connected to the positive rail. But also in this case, the circuit doesn't work as expected. As you can see, in fact, the counter doesn't increase of one step at every pulse, but seems to jump forward randomly. The reason is that, before the contact is established, the terminal bounces several times, producing multiple clock pulses. This well-known problem is called contact bouncing, and it normally happens also with switches and buttons. In this case, the issue can be greatly reduced by simply putting a capacitor in parallel with the clock input. But in a real situation, the bouncing problem requires accurate studies in order to be solved. But let's come back to our project. To provide a regular clock input, I will now use the Evergreen 555 IC in its classical astable configuration. I will not linger here on the description of this oscillator, because there are countless tutorials and schematics on the internet. The values of the component is not critical. I've used what I had in my drawer, but you can experiment with different resistor or capacitor values in order to obtain faster or slower countings. The output of the 555, pin 3, must be connected to pin 14 of the 4017. And so this is the complete schematic. For those of you not familiar with schematics, here is one of the possible layouts of the components on the breadboard. And this is my prototype ready for testing. I will now apply the power, and voila, an old-style LED chaser. The circuit is not critical at all. As a proof, it is working, although, as I see now, I forgot to connect pin 4 of the 555. Well, that's all for this video. Please let me know in the comments if you found it useful. As a last thing, I remember you to subscribe to my channel, and I invite you to stay tuned for my next projects. See you soon!